Alright, so looking at the problem here, just a reminder, we had the farmer, he had the fencing, that he was gonna try to have these 3 pens. He had 80 feet of fencing to construct 3 adjacent rectangular pens. We had the X and the Y. We found that the area was 3 times X times Y. And if you remember last week, we talked about these optimization problems. The whole purpose is to get whatever you're trying to maximize or minimize, in this case area, in terms of one variable. Unfortunately, this had 2 variables, X and Y, so we needed to kind of revisit the situation to try to come up with a way of relating those 2 together. And that constraint, so to speak, was the perimeter. The perimeter was 4x plus 6y equals 80. Solving that equation for y, we got this, and we were able to plug that in to our equation and then get a nice area formula. Area equals negative 2x squared plus 40x. Now, see if my marker will work this time. Hey, it does. We also, I think you might have it on your paper, we talked about, in all these optimization problems, we need to think about what are the boundary cases, okay? What's the smallest x value, what's the largest x value, okay? What values did we put down? I think, like, do y'all remember what our smallest x value was? We wrote 1, okay? So we have area is equal to negative 2x squared plus 40x, where x can be from 1 up into,
I think it was 74.
I think it was 74, because we said the biggest it could possibly be, let's just assume that y is 1, okay? So we have a very narrow, here, 1, 1, 1, 1, 1, 1. That's using up a foot, a foot, a foot, a foot, a foot, a foot. What's left over has to be x. Now we said that that would mean, obviously it would be a lot narrower than this, but then we said if you go up to 74. But if you look at it, that's not exactly entirely correct, because x is this, and this, and this, and, you know, all of that remaining portion has to add up to equal 74.
So 74 divided by 4.
74 over 4, yeah, that's a more realistic number, which is?
18.5.
Say again?
18.5.
18.5. Okay, so those are our candidates in terms of where the maximum area would be. Well, one is a candidate, 18.5 is a candidate, neither one of those endpoints. The way that we can find the only other candidate is to do is take the first derivative and set it equal to 0, or also find out where it doesn't exist. So the first derivative is negative 4x plus 40. Set that equal to 0. You end up with x equals 10. So what we want to do is the candidates test. So we'll write candidates test. Remind ourselves. X values and area values. 1, 10, and 18.5. Right? Right, so Harley, you plug in 1 into the area function, okay? Because we're actually plugging it into the variable function. Ivan, 10, James, 18.5. When you get a number, just let me know.
For 1, it's 38.
What would the units be on that?
Feet squared.
Yeah, I don't always say square feet. Okay. Ivan?
If I did 200 square feet.
Okay. James?
55.5 feet squared.
Which we normally would say square feet. I know it is feet squared, but the terminology says square feet. Okay, so which one of those gives us the biggest area? 10. Alright, that's an x value of 10. And then we can plug that in to this formula. Y equals negative 2/3 plus 40/3. And I'll just tell you right now that's going to give you 20/3. Or what is that? 6 2/3, so 6.67 feet for our y value. So they actually told us, they said that use the closed interval test, which is also known as the Candace test, to show that the total area is maximized when the dimensions of each pen are 10 feet by 20 thirds. Crazy way of writing it, I bet it is 6 2/3 or 6.67. Okay, feet. All right. You don't need to do any more guessing. You don't need to try other values. You don't need to say, oh, maybe we just make it a little wider, maybe make it a little bit shorter. It's done. This is the math. It's proven. We can go to the contractor and say, this is what I want my pen to be. How long I want it to be. Okay. Any questions? All right. Let's keep going. We'll apply these same techniques to some more problems here. This one says, if a rectangular box with a square base and an open top is to have a volume of 4 cubic feet, use the first derivative test for extrema to prove that the dimensions that require the least amount of material are 2 by 2 by 1. I'm more worried, rather than saying the first derivative test, I think our closed interval test is pretty good test here. Well, maybe we can do the first derivative test, I guess. I don't know, we'll see. Alright. So what are we trying to do? What are we trying to maximize or minimize, class?
The amount of material used.
The amount of material, okay? What would that correspond to on a box?
It would be the surface area.
It's the surface area. Now we've got an open top, so let's think about the surface area. We've got a bunch of rectangles and stuff like that. So the surface area is going to be the base, so x squared, and then we have 4 sides. Each side is x by y, so that's x times y plus x times y plus x times y plus x times y. So it's 4xy. Alright? Hence you get this formula here. We want to minimize the material, which is equal to x squared plus 4xy. Great. But what's the problem with this equation? What's that?
Is a y.
There is a y. Alright? So let's go over here and we need to think about what are our constraints, and we were told that it needs to have a volume of 4 cubic feet. Now the formula for volume is just the base x squared times the height, so y. That's where we get this over here, x squared times y equals 4. We can solve this for y by dividing both sides by x squared and get y equals 4 over x squared. So then we can take this value, and if you needed to draw an arrow to remind yourself what's going on, we're plugging that in for y. So we have x squared plus 4x times 4 over x squared. And get that equation right there. This gutter? Sure, what's up? I don't think I don't know if I've actually made the purchase yet. I can't remember. Let me give you a call back third period when I can look at my stuff. All right, thanks. So you can see that x cancels out that x squared, so we end up with x squared plus 16. They wrote x to the minus 1 because there's just a single x in the denominator there. Okay? Doing the first derivative here, that x squared turns into 2x. The 16x to the negative 1 turns into minus 16x to the minus 2. And then rewriting that with the x minus 2 in the denominator, we have 2x minus 16 over x squared. Alright, now let's see what they did here. They set that equal to 0. Okay, so we found the derivative, set equal to 0. 2x equals 16 over x squared. Multiply, 2x equals. Multiply both sides by x squared, we have 2x cubed equals 16. So x cubed equals 8, which means that x equals 2. Alright. X equals 2 is the only critical point. That's the only location where the derivative equals 0 or the derivative doesn't exist. Would y'all agree with that?
Mm-hmm.
Okay. Because, look at the derivative. It's just this thing. Well, I don't know. There might be a spot where the derivative doesn't exist. What about x equals 0? Right? What if we had a 0 right there? I'd say the derivative doesn't exist there either. Also, x equals 0 is that's a critical point. But I mean, I don't know. Does it even make sense to have x equals 0?
No,
Why not?
because you would need at least one to make like an area.
Yeah, at least 1 millimeter or something
Mhm.
like that. Yeah, okay. So, in all reality, we're looking at this from 0 up to, I don't know, maybe infinity. We really can't have an infinite amount of space, size for our boxes, but we'll put infinity there. So, x equals 0 is a critical point. Alright. Another way of kind of looking at this, they wanted us to do the first derivative test, so like our final play that game. So there's 0. We're not really interested also in anything negative. You can have a negative x value. Let's go ahead and look at the derivative. So I'll put m prime, and here's our number line. And remember, here is our derivative right here, 2x minus 16 over x squared. Let's plug in a value between 0 and 2, let's say 1, and let's plug in a value bigger than 2, let's say, I don't know, 10. So Rigel Harley, plug in 1, Ivan James, plug in 10, and we're doing our first derivative test, so all we really care about is whether or not this value is positive or negative. Harley, do you know what we're plugging it into?
Yeah, the derivative.
Yep. James, you got a sign for us? Positive or negative?
For which one? 1
No, for 10.
or 10? It is positive.
For 1, it's negative.
Okay. What does that tell us about the material function? If the derivative is negative, that tells us that the original function m is,
Decreasing.
say again?
Decreasing.
Decreasing. Mm-hmm. And then in this region here,
Increasing.
increasing. So this says that the material that you are using is decreasing from 0 all the way up to 2, but then afterwards your material would be increasing. Is it ever going to change again? Could it ever go from increasing back to decreasing?
No.
Why not?
It doesn't have another critical point.
Yeah, because there's no other critical point. So therefore we can say absolutely that when x equals 2 is going to give you the, I wouldn't say that x equals 2 is the absolute minimum. We could say the absolute minimum occurs at x equals 2. Because I mean, say 2 is the minimum, that's kind of ambiguous. We would say that the absolute minimum amount of material occurs when you have an x value equal to 2. And if you want to, we can plug that in to our formula to figure out what y is equal to. So y is equal to 4 over 2 squared, which is 4 over 4, which is 1. So when x equals 2, and y equals 1. And that's it, that's the math. We don't need to plug in different values, we don't need to experiment, anything like that. We know, and we have proven conclusively, that that's our best dimensions, that's our optimization. And that's the value of math. You don't have to, I mean, if you understand how this works, then it's not sort of foggy and mystical. If you want, maybe I need to try some other values, or maybe it'll change. No, we know this is the pattern. Okay? We know this is what's going on. Alright. Just wanted to kind of show you a couple more of these, the type of problems, how they set up, because I want to give you all a chance to do some of the setup yourself. This one has talks about there's a rectangular page of print, and you've got the margins, okay? And they're going to say use the second derivative test for extrema to show that the least amount of paper is used when the dimensions are 6 inches by 9 inches. This activity that we're looking at here is really designed to force you not only to find the maximum minimum, but then to try the different tests and to show, you know, what they are. I'm more interested in the setup and how they did. They're wanting to they'll have the least amount of paper, okay? So if this is your text, X and Y, and you've got 2-inch margins vertically and 3-inch margins on the side, or 1 inch or rather. Anyway, you're gonna have 1 inch here and 1 inch here, so this, or 1.5 and 1.5, so it's gonna give you 3, and 1 inch here, 1 inch here, it's gonna be Y equals 2. And then you can get this formula here, the big piece of paper, X plus 3 times Y plus 2. We've got a constraining equation right there. You can find the derivative, and then you can do some other things with that, okay? So, I want to get some problems for y'all to work and set this up here. All right, we can look back on that one. Let's look and see if we can figure this one out here. Rise will read number 6 to us.
One side of a rectangular lot is on a river and is not to be fenced. If there are 400 feet of fencing available, use the closed interval test to show that the maximum area is 20,000 feet.
Okay. So very similar to the pig pen problem. All right. What are we trying to maximize or minimize? Trying to maximize the area. Okay. So that's going to be just a rectangle, so X times Y. What's our constraint here? You can't have
400 feet.
400 feet of fencing. Now if you're going to have X here, and you're going to have X here, you make those determinations yourself, and Y there, then you'd have 2X plus Y equals 400. That's going to be able, you're going to be able to solve that for Y, plug that value into your area equation, take the derivative, and so on and so forth. Number 7, you can see, is very similar to that other box problem. This is a net enclosure for practicing golf, is to be open on one end. Here we want to show that the dimensions that require the least amount of netting. Once again, a surface area type thing, okay? And so they have we want to minimize the surface area, so you figure out a formula for that. Your constraint is the volume, which is that equation. You solve it for Y, plug it in, and then you can go ahead and go through there. Number 8 is more mathematical, geometrical actually. Says a rectangle has its base on the x-axis and its upper corners on the parabola, 12 minus x squared. Use the first test to show that of all such rectangles, the dimensions of the one with the largest area is 4 by 8. So this right here is our constraining equation, y equals 12 minus x squared. We want to maximize this rectangle, so that's going to be 2x, because if you've got this kicks out x, so the whole width here would be 2x by y. That's what we want to maximize. We want to maximize that area, and then right here, boom, y equals 12 minus x squared. That's your constraint equation. You can plug that in, find the derivative, set equals 0, and find your maximum. Okay. On your homework problems, I'm not going to specify use this test or use that test or whatever. For our purposes, really the closed interval test, the candidates test, is the best one. Find the endpoints, find the critical point, and go with it. Okay. Let me give you the problems here so you can start setting them up. Obviously, some of the setup is gonna be the same. Some of them are gonna be a little bit different. As it turns out, the setup is pretty much 90% of the problem here. Okay, so if I go through and set it up for you, then that's really, I've done the work for you. So I wanna give you some time to work on this, and I'll answer questions as you get them set up. Okay?
Are those work together or just on your own?
Yeah, absolutely, yeah, you can work as a table. So, remember kind of what we did, when if you've got a picture, or you need to draw a picture, then say this is X and this is Y, and write down what you need to minimize, write down what you need to maximize, find a relationship between those things, find those constraints. And I can, as you make progress on each one of these, maybe when you get an equation, call me over, I'll check it out for you.